Hello, very welcome back to our channel, and we continue our discussion with NGSpice, a free open source spice circuit simulator to design and analyze through simulation variety of circuits. And in that series, as you can see on your screen, we have got this bipolar single stage amplifier that we are going to design and simulate to understand its performance. So what you can see here, we have got this transistor that is BC546. So we need a model in order to simulate the circuit and design a circuit using this transistor. So we need a model for this transistor as numbered, and we'll get that from the manufacturer. I will explain you how to get that, obtain that model, and how to incorporate that model into your Spice netlist. And we'll also explain how we can create the netlist of this circuit and then perform some kind of analysis. So you can see now, we have already explained in a variety of our previous module how this circuit works. So essentially, this is a single stage BJT amplifier useful for audio applications, and it can be used for some other applications as well. So basic components of this circuits, you have this transistor which has got collector pin, base pin, and the emitter pin. The circuit is biased in the common emitter configuration because the emitter is connected to the ground here, and you apply input to the base emitter side of the circuit, and you take the output from the collector emitter side of the circuit. So that's why emitter is common with respect to base and the collector. Okay. And R3 is your load resistance. R1 and R2 are used to set the DC operating point of this circuit. So I'm not going to explain you the small signal analysis of this circuit. I'm not going to talk about how this circuit will work. I will just give you an overview because we have done that in our previous module. So if you are new, you are encouraged to refer to those modules. So here the emphasis and the focus is to use the NGSpice and create the netlist of this circuit and simulate to understand how this circuit will work. So here your C in is your input coupling capacitor that will couple your AC input to the circuit. C out is your output coupling capacitor to couple your output amplified signal to the load. Our load is the load resistance. The gain of this circuit, that is the ratio of output divided by input, is decided by the resistor R3 in parallel with R load. So you've got 10K in parallel with 100K. That is your gain offered by this circuit. You don't have any emitter degeneration resistor to provide the bias stability of this circuit. So you've got this VCC, which is connected to the R3 and R1 at these ends. And the VCC of 5 volt has been used. So this is a power supply, voltage supply, in fact, that will deliver a current, and hence there'll be a power into the circuit. Then you've got the input signal, which is V in. It has a DC value of 0 volts. So you don't have, because signal that is to be amplified is a AC signal. So you apply a sine voltage source, which has a start, value of 0, and it has a peak value of 1 millivolt. It has a frequency of 500 hertz. So half a kilohertz signal we are applying at the input, and based on the gain multiplied with this 1 millivolt signal will be the output of this amplifier. Obviously, the bandwidth of the circuit should be such that it will amplify the signal up to 500 hertz. Okay, so what we are going to do is that we will create the spice netlist for this circuit. How we do that? First, we label the nodes at different points in the circuit. For example, at the collector where the R3, one end of the R3 is connected and the collector of the transistor is connected, is labeled as INTC. Here, the node is labeled as INTB. You can use different labels also. For example, A, here you can call it B, or X and Y or something like that. Here you have in, that is the label of the wire. Here you have a label labeled as out. Here you have a VCC. Here you have a VCC, and that's how you will have that. So obviously, if you're not comfortable, but because our focus here is to create the Spice netlist, learn how to write the Spice netlist, how to understand the syntax, how to understand different commands, how to make sure these components and the devices are connected to each other, and how to understand their interconnection. If you want to uh, use the schematic editor software, so TCAD is the free software. You can use other Spice softwares as well. And then you can generate the netlist, and then you can use the NGSpice to simulate. So I will show you now how I have written the Spice netlist for this circuit. So obviously in several of our previous models, I have explained you through different circuits from simple to the medium level circuit, how to generate and create the Spice netlist. But here, this is the Spice netlist for this BJT amplifier. So you can see that the first line is the title of my Spice netlist. That is a bipolar. I'm saying this is a bipolar amplifier. Any line or sentence preceded by this asterisk sign is regarded as a comment with any spice, specifically NGSpice. So this is a comment which is telling that, okay, the name of the file is bipolar, BIP amplifier.cir. So always remember the Spice netlist has an extension of .cir or .sp. Now, the most important thing is that I am using the real circuit design here. I'm doing a real design of the circuit because I'm using the real parts from the manufacturer. So I'm using this BC546. You can simply type these numbers on a Google and get the data sheet of that. From the data sheet, you can understand this is the transistor, which is an NPN transistor. It is used as a small signal amplifier and also some other applications. I'm using it as an amplifier here. So in order to accurately design my circuit, I need to have access to its model parameters. So those model parameters are provided by the manufacturer of this device. So what I can do, I can simply again open the Google and type Spice model for BC546, and Google will give me different manufacturer's name, and all those manufacturers will give me a Spice model as shown over here. So you can see that the model starts with dot model line and it is ending here. So it starts from this dot model and it ends here. So you can also have this whole four lines into one single line, but for the readability purpose, I have used up to this sentence, and then I use the plus sign, which indicates my model continues here. So again, I stop here and then use plus sign. Again, I go up to this point. Again, I use plus sign. So from this dot model up to this end bracket end, I have the model parameters for the BJT 546. So the model, how to add that model parameters and the model into Spice netlist is like this. You start with dot model, then the model name. What is the model name I'm using? I'm using the BC546, specifically B type transistor. And then what type of model it is. So I'm saying the model type is NPN. Then starts the bracket in which I have these parameters which are ready-madely provided by the manufacturer. I just have to copy paste them here. So IS is the reverse saturation current in the PN junction of the transistor, which is having this value. Then there is this VAF, there is this beta factor, which is about 480. Remember, transistor is the beta is the current gain, DC current gain. We also call it as a HFE of the transistor. So beta is 480. So if my base current is, let's say, 1 micron, my collector current will be base current multiplied by this number, that is 480 micron. So that's the current amplification I will have. Then there are all these parameters. You can see that there is a like uh, capacitance and all those things. So if you want to understand each of these parameters, which is not needed for a while now. We'll just restrict our understanding to this beta factor 480. Then I say R3 is connected between node VCC and the collector, or VCC and the collector node INTC, which has a value of 10K. Then I say R1 is connected between VCC and INTB. So here is VCC and INTB. It has a value of 68K. Then I say R2 is connected between INTB and ground. So here INTB and ground. Then I define these capacitors C out and C in. You can see that these are the two nodes and the value. These are the two nodes and the value. You can refer to the schematic for the nodes. Then I say I have used the VCC voltage source, which is connected between these nodes, VCC and the ground. This is VCC here, the VCC and the ground. It has a value of 5 volt. Then I have input voltage source, which is connected between node I in and 0. So it is I in. Here is the voltage source. Let me show you right over here. I in and 0. It has a DC value of 0 because I am doing the AC analysis. I'm doing the amplification. I want to see the amplification. So I use, say, it is a AC voltage source, which has a 1 volt of amplitude. This I will use to perform the frequency response and to perform the sine transient analysis. I am saying that this is a sinusoidal voltage source. It has a 0 volt initial value and it has a peak value of 1 millivolt. 500 hertz is the frequency. And then I say our load is connected between node out and the ground at a value of 100K. Then I say I have one transistor Q1, which is BC546, which is having this convention. First comes the collector pin, which is connected INTC, which is connected to this node. Then comes the base pin, which is connected to the INTB. And then comes the emitter pin, which is connected to the ground. And this transistor name is the BC546B. So therefore, the SPICE will understand I am using this transistor for which the model is already defined right over here. So if you define the diode, again, you will explain the diode here, and then you have a model for the diode. Okay, if you have a FET, you will write the FET connection here, and then you will have to have a model for that. Then SPICE netlist is completed. I will have to perform analysis. For example, I can also do here, let's say .op is one analysis, that is operating point analysis. And otherwise, I'm going to perform the transient analysis. I'm saying perform the time domain simulation from 0 second to 10 milliseconds, because my frequency is about just 500 hertz. So I don't need such a long time. And steps are just 10 microns. So you can imagine from 0 second to 10 millisecond at the step of plot the data at every 10 microsecond. So you can see calculate how many data points I will have. It is 10 millisecond divided by 10 microsecond. Okay, so about 1000 data points I will have. Here again, asterisk sign allows me to understand that I am intended to do the AC analysis or the frequency analysis for this circuit, which I have disabled with the command for a while because I can perform one analysis at a time. If I want to perform AC analysis, what I will do, I will put the asterisk sign here, and which will disable the transient analysis, and then remove this sign from this analysis, which will perform the AC analysis of this circuit. And then I will add the command .end. This will make sure that my SPICE deck is completed. After that, I will just use the save as. I have to make sure that I have explained this in the previous module also. I have to store the file in the bin folder. So it is like BJT. I just give a name and then I say CIR. So I have already done that. So I will say that save it. And it is asking me, do you want to replace it? Yes, because I have already done that. So yes, my file is saved. Then I will open the NGSpice from my computer. This is the command interface. And you can see now on this place, I can load this file, which is saved in my bin folder to perform this analysis. So what I'll do, I will just say source bjt.cir. I have done that. Once that is done, you can see now this circuit bipolar amplifier, that is the title, has been loaded. Okay. Now what I can do, I have performed the AC analysis actually, because the transient analysis is disabled, but now I have performed the AC analysis. So what I need to do is plot the gain of this signal, that is the magnitude of this signal of the output, and the phase of at the output. So for that, I need some command. So let me find out and show you what those commands are. Okay, so what I'm going to show you now, the result of this AC analysis. We are running this AC analysis, and we'll see how the output looks like. We basically have to plot the output magnitude with respect to frequency, and the phase of the output with respect to frequency, and AC analysis will let us do that. Okay, so let us have this. So first I will load this file, which is the command is source, and the name of this file bjt.cir. With that done, I can now say, ask it to plot V of V out. That is the output voltage I will have. Oh, not V of V out, just the output node. You see, there is this out node, and that is what we have. On the schematic also, this is an out node we have. So we'll do that. And look at this. It is giving me that output, but the gain is like inverted right over here. So let me check that out. So just a second. Yeah, so what if we plot, for example, plot V of a decibel value of the magnitude. We just take the 20 log of the magnitude. So it is like out, and we'll see. Now it's good. Now it's showing that. So it's a typical response of a small signal common emitter amplifier. This is like a mid frequency range from about 100 hertz to about 10 to the power 5 hertz, 100 kilohertz. You have a very constant gain, about 40 dB. And then you are at low frequency and very high frequency, your gain drops. Okay, how about plotting the phase? So we'll say that plot pH of out, and that's how the phase is going to vary. You see now, over the frequency you have this phase variation. Okay, you want to label this y-axis and the x-axis, you want to label in this plot also. So there are additional commands you need to incorporate with the control deck. We have explained that in the previous model, so refer to that. How about, so with that done, we are done with the AC analysis. Now, how about we do the transient analysis? So let us enable this and disable this. So we are done with this transient now, and we'll see how things go. Save, load the file again. So up and down arrow on your computer, you can repeat the command instead of typing it again and again. So it is loaded now. And now you just say, okay, plot V of out. That's, oh, there's some issue here. We have to check it out. We don't want frequency response actually, but it is plotting that. So let us figure that out in a moment. Okay, so what you can do here, you can see that there's just remove the dot here. You don't need to specify dot. This is just a transient analysis, 10 micron, 10 millisecond, and then save it, and then just say source. You loaded the file and then ask it to plot, let's say plot plot V of in first. So that's your input signal. You see now it's starting from 0 to 1 millivolt peak. So it's like 2 millivolt peak to peak input signal. Then you can say, okay, plot out. That is input output of the amplifier. Here you see. So you have a gain of about 100. So you got 1 millivolt peak in the input, and here you got the inverted output, uh, minus 100 millivolts. So you have a gain amplification of about 100. That is a voltage amplifier. If you want to plot the two signals on the same graph, what you can do is simply say plot in space out. Let us do. You can do that. And look at this. The green is the input and red is the output. So that's how you successfully designed and analyzed through the simulation using NGSpice, your BJT amplifier, small signal amplifier. And most important point is this is a real design because you have used the real component and the devices, that is BC546. Just refer to its data sheet. So hope you found this video useful. If you did so, share it with others and stay tuned for more engaging contents like this. Till then, wish you happy learning.